It's a strange quirk of human language, isn't it? That sometimes, to really say what we mean, we have to say it twice.
Hmm.
And I don't just mean repeating yourself. I'm talking about things like hush hush or bye-bye, or even to and fro.
Right. It seems inefficient on the surface.
It does. Why use two words when one should do the job?
Well, if you think of language as just data, maybe it is. But, reduplication has this massive communicative function. It adds intensity, it adds rhythm. In a lot of languages, it's not just style, it's actual grammar.
And that is exactly where we're going today. We're looking at a language where this doubling up is, well, it's a fundamental pillar of how it's built.
We are.
We're diving into the Manipuri language, also known as Thailand, and a really fascinating paper called Identification of Reduplicated Multi-Word Expressions Using CRF.
That's the one by Kishorjit Nongmakapam and his colleagues. And it really bridges two very different worlds. You've got the rich, complex structure of a Tibeto-Burman language on one side.
And the cold, hard stats of machine learning on the other.
Exactly. They're trying to solve a very specific problem. How do you teach an algorithm to see two words and know, that's actually one single idea, especially when the language builds words in a way that's, well, completely alien to English?
And just so everyone's clear, this isn't some abstract linguistic puzzle. This is about the nuts and bolts of natural language processing. If you want Google Translate or any search engine to work for Manipuri.
A language spoken by millions.
Right. In Northeast India, Myanmar, Bangladesh, you have to solve this problem first.
You do. Manipuri is a Schedule 8th language in India, so it has official status, but in the digital world, it's what we'd call low resource. And the core challenge, the thing that makes it so tricky, is that it's highly agglutinative.
Okay, let's unpack that.
Yeah.
Agglutinated.
Yeah.
In English, we tend to keep our words separate. I am walking. Three little islands of meaning.
Right. Very isolationist.
But Manipuri is more of a fused language.
That's a great way to put it. In agglutinative languages, you build these really complex words by taking a root word and just sticking things onto it. Prefixes, suffixes. The amount of information you can pack into one string of letters is just incredible.
The paper points out something I found staggering. Most of the root words in Manipuri are bound. They can't just exist on their own.
They can't. They need an affix attached just to be a valid word.
Which, for a computer, must be a nightmare.
It's a huge problem. How do you index a word that can't stand alone? The affixes actually decide what kind of word it is. You can add one suffix and it's a noun, swap it for another, and suddenly it's a verb.
I really want to use the example they give in the paper because it just paints such a clear picture. The word is Pusin Hedi John, Pusin Hal Na Jin Joiko.
And you said that very well.
I practiced.
Mm.
But that whole thing is one word.
It is.
And the translation is a full sentence. I wish I myself would have caused a carry in the article. It takes 12 English words to unpack that one Manipuri word.
And if you break it down, the root is just pu.
Pu, meaning to carry.
Right. Everything else is just stacked on. Sin means in, sheen makes it causative, j makes it reflexive for myself, and it just keeps going. 10 different suffixes on one root.
The paper says there are 72 listed affixes in total, 11 prefixes, and 61 suffixes. And they could be stacked. So computers' vocabulary isn't just a list of words, it's this exponential number of combinations.
It creates what's called a data sparsity problem. A machine learning model needs to see examples over and over to learn a pattern.
But it might see a combination of suffixes it has literally never encountered before.
Exactly. So in the middle of all this complexity, the researchers are looking for something even more specific, these reduplicated multi-word expressions, or RMWEs.
Okay, so a multi-word expression, or MWE, is a phrase like kick the bucket.
Right. You can't understand it by looking at kick and bucket separately. The whole phrase is one unit of meaning.
And in this paper, they're looking at MWEs formed by repetition, reduplication.
The authors break them down into 6 different types, and I think it's really worth walking through them because repetition is, well, it's more nuanced than you'd think. It's not just hitting copy-paste.
Okay, so the first one is the most straightforward, complete reduplication.
An exact copy of a word.
The example is mumrik. Umrik means a drop.
So mamrik means drop by drop. It changes from a noun to an adverbial concept. For a machine, that's the easiest pattern to spot. Word A equals word B. Simple.
But then it gets trickier. The second type is partial reduplication. The example is non tholk, sin.
Which means to go to and fro.
So kond is the root for go or move. But the suffixes are different, thonk and sin. It's like saying go out, go in.
Exactly. The algorithm has to be smart enough to see that the roots are the same, even if the endings are different.
The third type is where it gets really abstract for me. Echo reduplication. This is where the second word in the pair is basically a ghost word. It has no meaning.
Right, you see this in a lot of South Asian languages. The example they use is "thi kasi," which means good manner.
Okay, so thiesi means good manner. What does kasi mean?
Nothing.
Nothing.
It has no dictionary definition. It's semantically empty. It's just there for rhythm to balance the phrase. Imagine being a computer trying to look that up. You'd find nothing.
It's like a structural crutch for the real word.
That's a good way of putting it.
Okay, then we've got mimic reduplication, which is just onomatopoeia. So kunk,
Kook, the sound of dry earth cracking.
and double reduplication, which is even more complex. It uses 3 words. The example, iman inun munba, means completely ripe.
Yeah.
It's like the repetition makes it a superlative. It's not just ripe, it's really ripe.
But the last category, the sixth one, is the real challenge for the tech. Semantic reduplication.
This is where you have 2 totally different words that mean the exact same thing put side by side.
The tiger example.
Right. Pamba means tiger. And Kong also means tiger. So the phrase Pamba Kong just means tiger.
So why do it? The paper explains it's a historical artifact. Different clans in Manipur had different words for things. As the language unified, speakers would use both words together to make sure everyone understood.
It's like a fossil in the language. It
Yeah.
preserves that history. But imagine you're the algorithm. You see Pamba, you see Kain. They don't look alike, they don't sound alike. There's no pattern.
The only connection is meaning, and that's invisible to a basic pattern matching system.
So this is the puzzle. You have these 6 types of repetition buried in this super dense agglutinative language. And the tool the researchers use to find them is called conditional random fields, CRF.
Yeah, CRF has been a real workhorse in this kind of task, what we call sequence labeling, for years. It's a type of statistical model.
Okay, so break that down. Why use something like CRF? Why not just write a set of rules? If word 1 equals word 2, then tag it.
Because rules are brittle. That works for complete reduplication, but what about the tiger one, or the partial ones? A rule would break. CRF doesn't use hard rules, it calculates probabilities.
So it's not just looking at one word in isolation.
No, that's the key.
It's looking at the whole sentence and asking, given the words around it, what's the probability that this is a multi-word expression?
Context, that's the whole game. The model looks for features, clues in the text, and the paper goes into a lot of detail about which clues are the most helpful.
The first one seems obvious, the stem word.
Right. They use a stemmer to strip off all those suffixes and find the root. If the roots of 2 adjacent words match, like in tektok, sin, that's a massive clue.
But the feature that seemed to have the biggest impact was the context window. They didn't just look at the word itself.
No, they looked at the 2 words before it and the 2 words after it, a 5-word window. That allows the model to learn the neighborhood where these expressions tend to live.
And because it's Manipuri, they had to deal with all the affixes. They actually counted the number of prefixes and suffixes on a word and fed that number to the model as a clue.
They even went deeper. They created features for up to 10 different suffix slots per word.
Wow, that's granular.
It is. It's essentially telling the model, hey, I've noticed that when a word ends in "go" and the next one ends in "go," they often belong together.
They also added some simpler things, right, like word length.
Yeah, basic heuristics. Very short words are usually function words, so they're probably not MWEs. And a digit feature, to make sure it doesn't flag the number 22 as a repetition.
Now, to train a model like this, you need good data. And I was really impressed by how they built their gold standard corpus. They didn't just scrape a bunch of websites.
No, you can't. That data is way too noisy. They used a corpus of 55,000 words that had been manually tagged and checked by linguistic experts. It's slow, expensive work, but it's the only way. You need a perfect answer key to train the system.
So they took 50,000 of those words for training, showing the model the answers, and then they tested it on the last 5,000 it had never seen before.
And the results were really quite good. The system got an F measure of 92.41%.
For anyone not in data science, the F measure balances how many it found correctly with how many of its guesses were actually right. So over 92% is basically a solid A.
It's a very strong result. But the really interesting part is when you break it down by those 6 categories.
Yeah, okay. I'm guessing the easy one, complete reduplication, got the highest score.
It did. That one and the mimic, the onomatopoeia, were up in the high 90s. Makes sense. The pattern is right there on the surface for the machine to see.
And the tiger problem, the semantic reduplication.
That was the lowest. It dropped all the way down to about 83%.
That's a big drop. And it confirms what we were talking about. Without that visual clue, that rhyme, the computer really struggles.
It does, because the connection is purely conceptual. Pamba and Kang are linked by history and meaning, not by their spelling. The CRF model is basically flying blind on those.
It's just relying on the context window at that point. Just, well, these two different words seem to show up next to each other a lot.
That's the only signal it has. And frankly, getting 83% from just that signal is still pretty impressive. It shows how powerful those context features are.
So, okay, we have a system that works over 90% of the time. What's the real-world application here? Why should the average Manipuri speaker care about this?
It all comes down to the usability of the internet and modern tech. When you type a search query in Manipuri, the search engine has to first break your sentence into meaningful units. That's called tokenization.
Right, breaking it into tokens.
Exactly. And if you search for Sinsin to go to and fro, and the system breaks that into 4 separate words.
The search results would be useless.
Total garbage. It needs to know that the whole phrase is one single concept. It's the difference between searching for New York versus searching for New and York.
Of course. And for machine translation, it must be even more important.
Absolutely critical. You can't translate Pamba Theniki as tiger tiger. A good translation system needs to identify that as a semantic MWE and just output tiger. Without this work, you get these literal nonsensical translations.
So this research is basically building a better pair of glasses for the computer to see the language properly.
That's a perfect analogy. And for a language like Manipuri, the glasses made for English they don't work. English tools look for the spaces between words. Manipuri tools have to look inside the words.
It really is a reminder that you can't just copy-paste a solution from one language to another.
You absolutely cannot. This paper proves that you need language-specific features, like counting the suffixes, to get this kind of high accuracy.
I think my biggest takeaway from this whole deep dive is how culture is sort of embedded in the code. We're talking about statistics and algorithms, but the hardest problem to solve was the history of the clans.
The semantic reduplication.
Exactly. It's like the language itself is resisting the machine's attempt to simplify it. It's holding on to that history of Pamba and Gang, and it defies simple pattern matching.
It's a beautiful kind of friction, isn't it? We're not just teaching computers to process data, we're trying to teach them to understand the collective memory of a culture. The fact that echo words even exist words with no job other than to provide rhythm, it just shows you that language is as much about art as it is about utility.
And trying to explain art to a conditional random field is a very tall order.
But 92% is a really good start.
It certainly is. This work is a huge step in making sure that as we move deeper into an AI-driven world, these incredibly rich, complex languages don't get left behind or flattened out.
It ensures they can stay functional and vibrant for the next generation of speakers.
So the next time you find yourself repeating a word for emphasis, or maybe you add a little nonsense rhyme to a word just because it sounds right, you should know you're performing a pretty complex linguistic function.
And somewhere out there, an algorithm is working very hard to figure out what you just did.
Let's hope it has a good context window. Thanks for listening to this deep dive.